Hey guys, the objectives for this video is to find the stress increase, the vertical stress increase, under a point inside a rectangle. So if we were to make up a quick example, let's say we had a rectangle. This is obviously in plan, so looking down bird's eye. So it's A, B, C, D. Let's say that this rectangle is 10 meters by 6 meters. So we want to find, say, the vertical stress increase at a point O. So let's put that point O there, and let's say that this point O will subdivide the rectangle into these shapes. Now whenever we're doing this type of example where we're finding a stress increase in a rectangle, we're always concerned about the corners of the rectangle meeting at our point we're interested in. So we're interested at point O. We need to ensure that all the shapes have corners at that point. So you can see this shape here has a corner at O, this one here is a corner at O, this one here is a corner at O, and this one here has a corner at O. It's not so important for this one where we're doing a point inside a rectangle. When we get to the next video where we're looking at a point outside a rectangle, it's going to become more critical. So let's go ahead and split this up. Let's say that this is now 8 meters, 2 meters, 2 meters, and 4 meters. And let's just give other points of definition. So let's call that point E, F, G, and H. Now, just like before, we're going to be using a graph, an influence graph. This one's a bit different, but you can see that we have values of M, N, and M, where M is on the curve and N is down here, which we're going to be using to find I. So let's just define these values N and M. N is equal to B on Z, which is a breadth of a rectangle divided by the depth. M is equal to L on Z, where L is the length of the rectangle and Z is the depth. These two values, N and M, are interchangeable. So what that means is, when you come and do this graph, N and M are completely interchangeable, right? So if you had an N here of a particular value and an M here of a particular value, if you swap those around on our graph, you'd still get the same I value. So don't be so concerned whether you use B or L, where B is the breadth and L is the length. They are completely interchangeable. So once again, say we have a profile of soil, and we have a rectangle, and we have a uniform stress of, say, 100 kPa. Okay, so we're going to now go and find the stress increase at a point here. Let's make Z equal to 4 meters. So 4 meters below the surface, at a point like this in plan of the rectangle, we're going to find the stress increase at O. So let's now break our rectangle up into these four shapes, which we have to do. So what we're going to do is we're going to find the stress increase of each of these shapes with a corner at O, and then we're just going to add all four up. So let's start with shape AEOH. So AEOH has dimensions 8 meters by 2 meters, which means we can find M. So M is the breadth on the depth. So the breadth of this is 8 meters on the depth, which is 4, which is 2.0. N is the, that is N. Once again, I don't really have to be so critical because they're completely interchangeable, but just for the example I will. N is 8 on 4. M is the length, so let's call that 2 on 4. Really doesn't matter which values I'm using, so we get 2.0 and 0.5. So now we come to this graph. So we had an N value of 2.0, so that would be around here. So that this is N, this line here. So 1, 2, once again, this is log scale. So we have 2 and 0.5. So we would go to 2, and M of 0.5 is given by this curve here. It says M equals 0.5 for this line. So we'd come 2 and 0.5. We'd come across. It gives us an I value of around 0.138. Okay. So I equals 0.138. We know now, exactly the same as the circle, I equals change on Z on P, where P is the pressure. So this equals change on Z on top of the pressure, which is 100 kPa, which means we're going to get a change in Z of 13.8 kPa. So we're going to do this again for all the other three shapes. So let's do EBFO. So EBFO, N is 2, okay, so this shape is 2 meters by 2 meters. So our N and M are actually going to be equal because N is B on Z, which is 2 on 4, which is 0.5, and B will be the exact same thing. So we have 0.5 and 0.5. Come back to our graph. So 0.2345. So 0.2345 is here, and 0.5 is here. So 0.5, 0.5. We'd come across, find that value. It's just below 0.1, so let's call it I equals 0. So let's just call it 0.1. It's pretty much 0.10. Okay, 0.10, which means that the change in pressure will equal 0.10 times the pressure. So 0.1 times 100, same formula here. So that'll be 10 kPa. We now need to do the other two shapes. We've done these two shapes. So let's do shape OFCG. OFCG has dimensions 2 by 4. So N, once again, it really doesn't matter what I'm doing. N, say, is 2 on 4, and N is 4 on 4. So 0.5 and N is 1.0. So we have 1.0 and 0.5. So 1 down here for N, and M is 0.5. Once again, they're completely interchangeable, so I could have done it the other way around. We get a value of 0.12 roughly. So I equals 0.12, which means we can find our change in stress is 0.12 times 100, which is 12 kPa. And the last shape we need to do is this OHDG, which is 4 by 8 meters. So if we quickly draw this, so it's 4 by 8, and the numbers were the letters were H, O, G, D. So M, let's say it equals 8 on 4, which is 2.0, and N will equal 4 on 4, which is 1.0. So 1.0 and 2. So we are at 1, and we're going all the way up to 2. This last value is 3. So 2 will be around, roughly somewhere around, say, there, on the curve there. We'd then come across, and we'd get 0.2. We're getting around 0.22. So I equals 0.22, which means that the change in stress, once again, is equal to I times P, where it's 0.22 times 100. So it's 22 kPa. So now what we're going to do is to find the total stress increase under O, we're going to add up all these values we found. So the total stress increase will equal 13.8 plus 10. So 13.8 plus 10 plus 12 plus 22. And if we were to calculate this, so 13.8 plus 10 plus 12 plus 22, we get 57.8 kPa. And this, once again, is a vertical stress increase. It's not the final stress we're getting, it's the increase due to this. And the reason that this definition is important is because when we come and find the settlement now, we know, say that the total, say we have an initial stress of 20 kPa. The final stress is not 57.8, it's 57.8 plus the initial. Okay, so it'll be 77.8. So once again, this is a stress increase. It's not the final stress, it's an increase. So we need to add that to our initial stress to find the final stress, which is an important definition, because when we come and find settlement, which we're going to be doing in a couple of videos time, where I'm going to go through a very comprehensive example, you just need to have that distinguishing feature, that is the stress increase. But anyway, we've just done now, we've found the stress increase at a point O, which is inside a rectangle. We found that to be 57.8. Just another important thing is that it's always at the corner, and when we do the next example where we're going to be finding a point outside the rectangle, that definition is going to become important. Anyway guys, hope that helps, and we'll see you in the next video.